In this video lecture, we will examine the solutions of the groundwater flow equations for uniform recharge or leakage, aka uniform net specific discharge. Here is a little sketch of the problem under consideration. We are thinking about the case of an aquifer that has a steady flow of water through it, meaning that the water has a constant velocity. Additionally, water is going to be added to or subtracted from the aquifer. That would be recharge. This would be leakage. And that is going to happen. It'll be pretty slow, but we're going to let that happen and see what the mathematics to describe this situation would be. Before we go any farther, it's time to review the general equations for 2D flow laid out in a previous video. Basically, the general equation says that the second spatial derivative of hydraulic head, think of it as the curviness of the hydraulic gradient, plus the net amount of water flowing into or out of our system in the vertical dimension, is related to the ability of the medium to store water and the change in the hydraulic head with time, right? And then, of course, this all also depends on the transmissivity of the medium, which is physically just the same thing as hydraulic conductivity. Just remembering that T, transmissivity, equals conductivity times the thickness of the aquifer. All of this should make sense, right? If you keep adding or subtracting water to or from an aquifer, then you would expect the curvature of the hydraulic head might vary spatially. For example, maybe you'd have drawdown at a well, right? So you have some spatial variation. Or you might expect it to vary with time. After a storm, you have a lot of input, and that's going to raise your hydraulic heads because you've added water. So just on a physical level, this equation should make sense to you. Now, in the specific example that we are choosing to describe, we have some recharge or discharge, right? So this N here, that's non-zero, right? It's going to stay there. It's not equal to 0. And if we have steady flow, that means there's no change to the hydraulic head. There's no change to the potentiometric surface with time. So in that case, this part of the equation does equal 0. And we are describing steady flow like so. So just to make sure that we're all on the same page, think about turning on a pump and waiting until the system achieves steady state. When you first turn on the pump, there would have been some change in head with time, but after you've run that pump long enough, then the system re-equilibrates and hydraulic head no longer changes with time. So that would be the type of situation that we would investigate with this equation here. So just to restate this, we have the curvature of the gradient of hydraulic head equals the net specific discharge divided by the transmissivity of the aquifer. So the amount of water moving vertically into or out of the aquifer and the ability of the aquifer to transmit that fluid. And from this relationship, we get equation 7.12 in the textbook. It looks like this, with D defined as follows right here. Now, D is a parameter that describes the flow geometry. When D is equal to 0, flow is one-dimensional in the y direction, like so. Here we have the black lines are the head contours, and these blue lines are the flow lines indicating the direction of water flow, and all of the flow is happening in that y dimension, making this the 1D solution in the y dimension for the case when d equals 0. Now, as we increase d, we see some curvature, and we see the flow extending into both the x and the y dimension. And we can increase that curvature more at d equals 0.5. It actually is going radially outward. And if we keep increasing, then eventually we will get to the case of d equals 1. And in that case, all of the flow is in the x dimension, and you have 1D flow in the x dimension. Now, it's important to recognize that utilizing a D of 1, for example, over here, this doesn't mean that your flow actually splits in the middle here. Instead, D equals 1 is just describing the head changes that you see in the geometry, including any subsection. Okay, so for example, if we have horizontal flow like is shown here, then this is represented by the case of d equals 1 because we can find this solution over in the geometry that described the d equals 1 case. Okay, so just because you have, while the solution can describe bifurcations, it doesn't have to. All right, so for example, d equals 1 is the general solution for one-dimensional flow in the x direction. And while we're on the topic, let's go ahead and make sure we all understand how to calculate d. First off, the equation here, well, that only works when d is in 2 dimensions, when it's an ellipse. For the case of flow, 1D flow in the y direction or 1D flow in the x direction, in those two instances, d is not an ellipse, right? So in the case of 1D flow in the y direction, d would actually just be set equal to 0. And for 1D flow in the x dimension, you're going to set d equal to 1. It's only when you have flow in both dimensions that you're going to need to use the equation to calculate d. Now, here is a flow pattern for which we could calculate d. Technically, we do need a scale bar so that we can measure the change in distance from one head contour to another. However, because these are both circles, the distance traveled along the x-axis from the inner to the outer circle is going to be the same as the distance traveled along the y-axis from the inner to the outer circle. So that means that delta x is going to actually equal delta y. So if you take delta y dx, that's 1 divided by 1 plus 1 equals 1 divided by 2. So in the case of concentric circles, d equals 0.5. Now, for an example of how to calculate d from a potentiometric surface map that includes actual numbers for hydraulic head and real non-zero values for the distances between head contours, which you can read from the scale bar here. For that, you can go ahead and see example 7.3 in the text. That is on page 255. Okay. Now that we're comfortable with d, we should practice utilizing this equation for hydraulic head, equation 7.12. To make things a little simpler, I'm going to go ahead and set d equals 1 to model 1D horizontal flow in the x dimension. Now, if we consider a specific location in our system, for example, if we put x equals x naught at our well here, x equals x naught, then this will give us the value of then this equation will give us the value of hydraulic conductivity at x naught, right? So we'll call that h naught, the hydraulic head at x equals x naught equals this. Now, if we know the recharge rate N, then we ought to be able to determine the transmissivity of flow through the aquifer if we can compare the hydraulic head at two locations. So you might have one location at x naught and some other location some distance x away. So I'm going to say that at the well here at x naught, I'm going to set x naught equal to 0 actually, and then the some distance away, we'll call that x, we'll just call it x, okay? So we're going to have a hydraulic head at the well, h naught, at a distance of 0, and farther away at a distance x, we'll have some other hydraulic head, which we will just call h. So here we have that, our equations for hydraulic head at the well and hydraulic head some distance away from the well, okay? So at this point we have two equations and two unknowns, right? Assuming we know the recharge rate and we want to find this transmissivity, but we also need to know what C is, right? So C was just that parameter that sort of moves the water table up and down, but we still need to know what that is in order to solve this system of equations. So what we can do is we can actually solve for C in this simpler case of x naught being 0, and once we figure out what C is, we'll be able to turn around and plug that C in to this equation for hydraulic head. So rearranging to solve for C is over here, and then recognizing that x naught, the head at the well, is at a position of 0, we're going to have C equals h naught, which we plug in for C, right? So that gives us this equation here. And of course, we can rearrange, bring that hydraulic head over here, and end up with our final useful equation for trying to figure out how hydraulic head changes in relation to steady inflow or outflow in the vertical dimension, and how that relates to the transmissivity of the aquifer. So there you have it, the equation comparing hydraulic head at 2 points for the case of steady horizontal flow in a confined but leaky aquifer. This concludes the uniform recharge/leakage lecture video. See you next time.